Hello, calculus friends. This is section 4.5, day 1 notes. When we first started studying limits at the beginning of the school year, we learned that there were things called indeterminate forms, like 0 over 0 or infinity over infinity. Remember when we sorted our limits into 3 piles, type 1, type 2, and type 3? And these were the type 3 pile where we couldn't evaluate it with direct substitution, and there was no algebra that we could do. There was no rationalizing or simplifying or foiling or distributing or anything that would help us figure out the limit. And so then our only options at that point were either to make a table and or a graph and just examine what was happening right around the area, wherever the x value was that we were trying to determine the limit. And so in those situations, that was all that we had. Well, today we're going to learn a systematic method for evaluating these types of indeterminate forms of limits. And this systematic method that we're going to learn is called L'Hopital's rule. And L'Hopital's rule says, suppose that f and g are differentiable and g prime of x does not equal 0, okay? And the reason is because g of x is in the bottom, all right? Suppose that the limit as x approaches a of f of x is 0 and the limit as x approaches a of g of x is 0, or that those limits are positive or negative infinity and positive and negative infinity. So basically, that means that when we plug in our x value, we get an indeterminate form of either 0 over 0 or some form of infinity over infinity. What L'Hopital's rule says is that if we take the derivative of the function in the numerator and the derivative of the function in the denominator, as long as the derivative of the function in the denominator does not equal 0, then the limit of the derivative of f over the derivative of g will give us the same result as the original limit would. And we can continue to use L'Hopital's rule as many times as we need to in the same problem as long as we still have an indeterminate form till we get to the point where eventually, we get an answer that is not infinity over infinity or 0 over 0. So I think that the best way to do this is just to jump in and try it. So what we have to keep in mind when we're thinking about using L'Hopital's rule is that we have to check first to make sure that we have an indeterminate ratio, okay? And I really want to stress this. You cannot assume, you must check, okay? You must show that you've checked before you apply L'Hopital's rule. And if you're going to use L'Hopital's rule on the AP test, they are going to be looking for some sort of proof that you checked that the numerator and denominator created an indeterminate form before you applied L'Hopital's rule. So here's how I like to show it. In our first example, example 1, if I were to plug x equals 1 into my numerator, 1 squared is 1 and 1 minus 1 would be 0. So I checked that if I plug 1 in, I get 0 in my numerator. And in my denominator, 1 squared is 1 minus 1 is 0. So I get 0 in my denominator. So I'm showing here that by direct substitution, my numerator goes to 0 and my denominator goes to 0, and that I have the indeterminate form 0 over 0. So now I am going to apply L'Hopital's rule. So I just write LR, L'Hopital's rule, and I show that that's what I'm doing. So I'm still going to have the limit as x approaches 1, but now I'm going to take the derivative of my numerator. And the derivative of x squared minus 1 is going to be 2x. And I'm going to take the derivative of my denominator. And the derivative of x squared minus x is going to be 2x minus 1. And now if I plug in x equals 1, my numerator and my denominator no longer go to 0 over 0. So now I can actually evaluate my limit using direct substitution, which is going to be 2 times 1 over 2 times 1 minus 1, which is going to give me 2 over 2 minus 1, which is 2. Okay, so the answer to the limit in example 1 is 2. But up until right now, and I guess that one we could have done with some algebraic manipulation, right? We could have factored our numerator and factored our denominator, factored out the x minus 1 factor, and we would have been able to do it that way, but this was a great example to show L'Hopital's rule with. All right, so now let's take a look at example 2. If we were to plug 0 in our numerator, 4 times 0 is 0, and the sign of 0, now think unit circle, 0 is the start of the unit circle. The sign value of the ordered pair is the y value. The ordered pair at the start of the unit circle is 1, 0, so sign of 0 is 0. So my numerator goes to 0. And remember that tangent is sine divided by cosine. So if sine is 0, then tangent is also going to be 0. So my denominator goes to 0 as well. So I am going to apply L'Hopital's rule. Now this is going to require us to use chain rule because inside of our sine function we have 4x and inside of our tangent function we have 5x. So keep in mind that when we use L'Hopital's rule to differentiate, we have to differentiate the outer function at the inner times the derivative of the inner, which is the definition of chain rule. So the derivative of sine is cosine. So my numerator, I still have the limit as x approaches 0, but then my numerator is going to be cosine of 4x times the derivative of 4x, which is 4. And in my denominator, the derivative of tangent is secant squared of 5x times the derivative of 5x, which is 5. And I'm going to do a little algebraic trick right now. In my denominator, I have secant squared 5x. And since it's in the denominator, it's 1 over secant squared. But secant is the reciprocal of cosine. Okay, so basically, this secant squared of 5x in the denominator is the same as cosine squared of 5x in the numerator. And I always like to think in terms of sines and cosines if I can, if possible. So I'm going to rewrite this as the limit as x approaches 0 of, I'm going to put the 4 in the front. I still have the cosine 4x. But then I'm bringing the secant squared 5x upstairs and renaming it cosine squared 5x. And that 5 is still in the denominator. All right, and now I can actually evaluate my limit. If I plug in x equals 0, I have 4 times cosine of 4 times 0, well, 4 times 0 is 0. Cosine of 0 is 1. And 5 times 0 is 0. Cosine of 0 is 1, and then 1 squared is 1, right? Over 5, which gives me an answer to my limit of 4/5. Example 3, there's a little asterisk next to it. The limit as x approaches pi from the left of sine x divided by 1 minus cosine x. The reason that there's an asterisk in front of it is about to be relevant here. If I plug pi in, think of the unit circle. Pi is halfway around the circle. The ordered pair at pi is -1, 0. So sine of pi would be 0. Cosine of pi is -1. So here I would have 1 minus -1, which is 1 plus 1, which is 2. So do I actually have an indeterminate form here? The answer is no, I do not. This limit can be calculated by direct substitution. I can just do sine of pi over 1 minus cosine of pi, and I'm going to end up with 0 over 1 minus -1, which is 0 over 2, which is 0. And the reason that I included this on here is because I want to caution you, once you start using L'Hopital's rule, it's easy to get carried away and to stop remembering to check first, okay? So the moral of example 3 is this was not an indeterminate form. Always check first. Before applying L'Hopital's rule. Because the problem is, if you apply L'Hopital's rule when you don't have an indeterminate form, you will not get the correct answer to the limit. It only works for indeterminate forms. All right. The next part of our notes talks about indeterminate products. Okay, we just had indeterminate ratios where we had 0 over 0 or infinity over infinity. But what if we have a limit like x approaches infinity of f of x times g of x? And we get an indeterminate product, such as infinity times 0. In this situation, if we can rewrite the product as a quotient, we can still use L'Hopital's rule. Okay, so let's explore that a little bit with example 4. First, let's check and see what we get if we do direct substitution. So if we were to directly substitute x equals infinity in for x times sine of pi over x, we would get infinity here. And then if we plugged infinity in, pi divided by infinity is 0, right? Because anything divided by infinity goes to 0. So pi divided by infinity would be 0. So we'd have sine of 0. And we know that the sine of 0 is 0. So we end up with this indeterminate form, infinity times 0, which I don't know what that means, but it's not anything that we can get an answer from. So now we can say, okay, well, let's try rewriting this so that we have a quotient instead, because we need a quotient to apply L'Hopital's rule. So I still have the limit as x approaches infinity. And I'm going to leave the sign of pi over x as the function in my numerator. But I'm going to rewrite x times that as sine of pi over x divided by 1 over x. So basically, I just did a keep switch flip on it, right? Multiplying by x is the same as dividing by 1 over x. But now, when I do my check, if I were to plug in infinity, pi divided by infinity is 0, so sine of 0 would go to 0. And in the bottom, 1 divided by infinity would go to 0. So now I have a limit of the indeterminate form 0 over 0. So now I can apply L'Hopital's rule. And when I apply L'Hopital's rule, I'm going to be doing the derivative of the numerator divided by the derivative of the denominator. Okay? So let's see here. In my numerator, the derivative of sine is cosine. So I'm still going to have, I'm going to start over here, I'm still going to have the limit as x approaches infinity. But then I'm going to have cosine of pi over x. But be careful, this is chain rule. I have to multiply by the derivative of pi over x. We have to think of pi over x as being pi times x to the negative 1 power. So if I differentiate that, I bring down the negative 1, it becomes negative pi x to the negative 2, or negative pi over x squared would be the derivative. Okay, that's my numerator. And then in my denominator, the derivative of 1 over x, again, 1 over x is x to the negative 1 power. So bring down the negative 1 times x to the negative 2 is going to be negative 1 over x squared. Okay? But something to notice here, if you haven't seen it, let me point it out to you. These are very similar, right? I have a negative, and then I have an over x squared. And in the numerator, pi is just a coefficient. And we have learned that coefficients do not affect the answer, right? They just come along for the ride when we're differentiating. So I can actually take that pi and I can pull it out and put it in front of the limit. So this is going to be equal to pi times the limit as x approaches infinity of cosine of pi over x times 1 over x squared over, negative 1 over x squared over negative 1 over x squared. And now I can cross those out. And so now I have pi times the limit as x approaches infinity of cosine of pi over x over 1, which is just cosine of pi over x. So now when I plug in infinity, pi divided by infinity is 0. Cosine of 0 is 1, right? Because this ends up being pi, that's the pi in front of the limit, times the cosine of 0. And cosine of 0 is 1, so I end up with pi times 1, which gives me an answer to my limit of pi. Our last example, example number 5, is another situation where we have an indeterminate product. But again, we need to show that we have an indeterminate product first. So if I were to plug in infinity, infinity squared, well, that's still infinity, right? And then e to the negative infinity squared, that would be like 1 over e to the infinity squared. And e to the infinity would be infinity, and 1 over infinity would be 0. So this term is 0. Okay? So once again, I'm going to try to write this as a quotient instead of as a product. And this time, since the e term has a negative exponent, it's really easy to just move that one down to the bottom. So I'm going to rewrite this limit as the limit as x approaches infinity of x squared over e to the, and now it will be positive x squared because I moved it downstairs. So now if I were to do direct substitution with my infinity, I would have infinity on the top and I would have infinity on the bottom. And infinity over infinity is an indeterminate form that allows us to use L'Hopital's rule. So now we're going to take the derivative of the numerator and the derivative of the denominator. So this is going to be equal to the limit as x approaches infinity of 2x over the derivative of e to the x squared. This is going to be chain rule, is going to be e to the x squared because the derivative of e to the x is e to the x, but then we have to multiply times the derivative of our exponent x squared, and the derivative of x squared is 2x. Okay, but hey, look at that. 2x in the top and 2x in the bottom. Those are going to cancel out. So we are left with the limit as x approaches infinity of 1 over e to the x squared. And now we can do direct substitution because we're going to have 1 in our numerator no matter what. And then e to the infinity squared is just infinity. And 1 divided by infinity makes the answer to our limit 0.